is our g of x function, and we want to find the area between these curves between x equals a and x equals b. So essentially what we're finding is this area right here. Okay. Any ideas on how we might do this? Okay, integral, that's a good start. Okay, so integral, what do you think our bounds are going to be? From a to b. Okay, and if I only want this purple sliver, what do you think I should do?
Subtract.
Okay, take what and subtract it?
Minus g.
Yes, good. F of x minus g of x. You're exactly right. Dx. This is the formula for area between two curves. And what I want to point out here is that whenever we're working in x's, we take the top function. That's a really bad marker, so let's maybe not use that ever again. Okay, this is the top function. We called it f of x, and this bottom function is g of x. So whenever we are working in x's, we want to integrate top minus the bottom. Okay, is that clear? All right. Well, what if we want to work in y's? So let's say that I have some function here, call it f of y. Okay, and I have some other function here, let's call it g of y. Okay, and I want to find the area between them. So this area right here. Okay, and let's call these y coordinates, let's call this y equals c, and let's call this y equals d. And the reason I don't use a and b again is because I want to emphasize that whenever we are working in y's, we need to use y coordinates. Okay, so these are y coordinates, which would be different from the x coordinates. Okay, obviously. So what do you suggest that we would do here? The integral from c to d of what? F of y minus g of y, dy. Okay, so if you had to talk about direction or orientation here, f of y would be which function? The one that's on what side?
The right.
The right. Okay, and g of y would be the function that is on the left. Okay, so that's going to be a very important concept as we talk about area and volume, is that whenever we're working in x's, we're going to integrate the top function minus the bottom function. And whenever we're working in y's, we're going to integrate the right function minus the left function. Okay, so try to get that into your head as we kind of move along here. Okay, so let's work some examples. We're going to start off without our calculator. And so we're going to kind of go back and forth today between using our calculator and not using our calculator. We need to know sort of how to do both. Okay, so it says find the area bounded by the following graphs, draw a figure, and shade the bounded region. So I'm not trying to be perfect here, we're just trying to get a graph, right? So y equals 3 minus x squared. What does that look like?
Upside down.
Upside down parabola moved up 3. So upside down parabola moved up 3. So this is the point 0, 3. Okay, and then we have another function, y equals negative x plus 1. And what sort of a function is that? It's a line with a negative slope that's moved up 1, right? So it's going to look something like this. Okay. All right, so do you see the area that we're trying to find? The area bounded between those two functions, which is right here. Do you notice that this is definitely top minus bottom? So notice that when I draw those vertical lines, I'm always hitting the same top function, and I'm always hitting the same bottom function. Do you see it? That's a very important point, because if at some point I hit a different top function or a different bottom function, now we got to use two integrals, okay? Because our top function and our bottom function always have to be the same in the same integral. Does that make sense, sort of what I'm saying? Okay, it will later on when we work a different problem. Okay, so if we want to find this area, then this is going to equal to the integral of the top function minus the bottom function. So which function is on top? Yeah, the parabola. So 3 minus x squared minus the bottom function, which is negative x plus 1 dx. Okay, now the last thing I'm missing are what? Bounds. Okay, so to figure out the bounds, pretty much what we need to do is figure out what are these intersection points, and how can I figure out what those intersection points are without my calculator? Set the equations equal to each other and then solve. Okay, so that's the objective here. So maybe off to the side of the paper, 3 minus x squared is equal to negative x plus 1. Okay, I recognize this as a quadratic equation, so I'm going to move everything to the right-hand side because I don't like the lead coefficient to be negative. I like it to be positive, so I'm going to move everything this way. So I'm going to subtract 3 and add x squared. Okay, and so that's going to be 0 is equal to x squared minus x minus 2. Okay, now we got to dust off our factoring skills. So we need factors of negative 2 that add to negative 1.
Negative 2 and 1.
Minus 2 and positive 1, I think. And so x is equal to what? 2 and negative 1. Okay, so what are our bounds on our integral going to be? From negative 1 to 2. Okay, so far so good? Okay, now we're actually going to compute this integral by hand. Okay, so the first thing I'm going to do is distribute that negative sign and then collect the like terms. So what do I have going on? 3 minus 1 is 2. And then negative x squared minus, there is no x squared here, so that's just going to be minus x squared. And then minus negative x becomes positive x. Okay, so that's just me collecting the like terms, and now I need to use the fundamental theorem of calculus to evaluate this. So I need an antiderivative first, which will be what? 2x minus a third of x cubed plus a half of x squared, evaluated from negative 1 to 2. Okay, now what? Plug in the upper bound. Okay, so I'm going to do some arithmetic here in my head. 2 times 2 is 4, minus a third of 2 cubed is 8 thirds, and plus a half of 2 squared is 2. So that's what I get when I plug in the upper bound. And then I subtract and I plug in the lower bound. So 2 times negative 1 is negative 2. Minus a third of negative 1 cubed, well, negative 1 cubed is negative 1, times negative a third is plus a third, and then plus 1/2 of negative 1 squared is plus a half. Okay, and then I'll leave it to you to do the rest of the arithmetic. But I just want to kind of show you the setup, right, and how to get to the answer. Okay, so we should probably calculate that for the notes, though, so maybe grab your calculator and punch that in real quick. Okay, any questions here on part A? So this is by hand with no calculator. Got to find my bounds using algebra. Got to be able to do a definite integral without my calculator using fundamental theorem of calculus. Is that clear? Okay. Okay, were you able to calculate it, Nyla? Okay, you need me to, can I erase this?
Yeah.
Okay. Okay, so letter B, we have x equals 5 minus y squared, and x equals y minus 1. Now I know that we're not really accustomed to graphing equations that say x equals, and to be honest with you, the AP exam doesn't really put a lot of these on here, but I have seen a couple. Okay, so it's a good idea for us to at least chat about how to graph something like this. Probably the easiest way is just to plot some points and see what's going on. So for instance, if y equals to 0, what is x? It's 5, right? So I know that the point 5, 0 is going to go on there. And then I know that this is going to look like a what? A sideways parabola that opens that way, right? So it's going to look something like this. Okay. And then x equals y minus 1. Okay, well, if y is 1, we know that x is 0, so 1, 0 is going to be on this particular graph. What else is going to be on this graph? What if x is 0? What is y? Y is 1, right? So 0, 1 is also going to be here. Okay, and so this is going to be a linear function that goes through those 2 points, like that. And so now can you see what the area we want is? Okay, now if I were going to do this, obviously I want to do this in y's because my equations are already in terms of the variable y. So this is what we're doing, right minus left. Okay, and so there's our area. Okay, so this is going to be the integral. We're going to do this in y's right now, so dy. And which way do we integrate when we're doing y's? Right minus left. Okay, so the right-hand function is what? The parabola, so that's going to be 5 minus y squared, minus the left-hand function, which is the line, and that's going to be y minus 1. Okay, so now, what's the last thing that we need before we can move on? Our bounds. So we're going to get them in the same way as we did before. We're going to set the equations equal to each other. So 5 minus y squared is equal to y minus 1. Okay, again, I recognize it as a quadratic, so I'm going to move everything to the right-hand side. That's going to give me 0 is equal to y squared plus y minus 6, I believe. Okay, so that, what are we going to have if we factor this? Y plus 3 and y minus 2. So that y equals -3 and +2. Okay, so my lower bound over here is going to be -3, and my upper bound is going to be +2, and now I would solve this in almost exactly the same way as I did the previous example, right? So I would distribute my negative. So this is going to be what? 5 minus -1, 6, and then minus y squared, and then minus y, is that right? Okay. So if I'm doing this by hand, what do we need to do next? Antiderivative, okay, which is going to be 6y minus 1/3 of y cubed minus 1/2 of y squared, evaluated from -3 to 2. And now we're going to plug in our upper bound first, so that's going to be what? 12 minus 8/3 minus 2. Okay, subtract and plug in the lower bound, and so what is that going to be? -18. I think it's going to end up being +9 when we plug in a -3 there, and then that's going to be minus 9/2. Okay, now obviously on FRQ, we're done, right? There's nothing more to do here. On multiple choice, we'd have to be able to do this pretty simple arithmetic, okay? I'm not going to do it just for the sake of time, but Nyla, if you don't mind, just go ahead and calculate that so we have it on the notes for completeness, okay? Is it clear how to do this? Okay, on these two examples, it was pretty obvious. Should we work in X or should we work in Y, right? It was obvious because of the way our equations were set up. It's not always that obvious, and a lot of the times you have a choice, and so it's up to you to make the better choice, okay, whether you want to work in X's or Y's. Okay, so part of your homework will be you sort of exploring that decision, but we'll also talk about it in the notes as well. Okay, so next page. Now is when we are going to start utilizing our calculator. Okay, so it says let f and g be the functions defined by that and that. Let r and s be the two regions enclosed by the graphs of f and g shown in the figure. And then it says to find the sum of the areas of regions r and region s. Okay, and I'm going to show you two different ways to do this. Okay, so I'm going to draw a vertical line here to sort of indicate we're going to do this two different ways. And whichever way you do it is completely up to you. The first thing that has to happen, okay, is that we have to plug these functions into our calculator. Okay, so I'm going to come over here to my calculator, go to y equals, delete out what I had in there from yesterday, and type these in. So the first one says 1 plus x plus e to the x squared minus 2x. And then g of x is x to the fourth minus 6.5x squared plus 6x plus 2. Okay, so I've got both of those guys plugged into y1. And now what I want to do is I pretty much want to be looking at the picture that they have given me on the paper. So I need to pick an appropriate viewing window. It looks like their viewing window, I would say, starts at about -1 or so. And then I see that the right-hand intersection point, so let me show you what I'm talking about. This right-hand intersection point is at 2, right? So if we just go a little bit further than that, we'll be able to see their picture. Okay, so maybe like 3 on our x-max. And then on our y-axis, what do you guys suggest? Maybe like -1 to 5, right? That sounds like a pretty decent window. Okay, and so here's what we're looking at. Okay, so we can see pretty well exactly what they got, right? So if we want to find the sum of the areas of R, let's first of all find area of R. And so the area of R is going to be the integral, and so R is here. Okay, well if I do top minus bottom here, that means I'm going to work in which variable? If I do top minus bottom. In variable x, which is really good because if I work in y, that means I have to solve my equation for x. And look at your equations and tell me if that sounds like fun. Not very much fun. Okay, so it's a good idea here to do top minus bottom. So the question is, in region R, which function is on top? The second one, right? Which was g of x, correct? So I'm just going to write down g of x, okay, minus what function is on bottom? F of x. Okay, so, and we don't have to recopy down what they are. We're just allowed to call them what the problem called them, which is g and f. Okay, well, now what do I need to do? I need to figure out what these intersection points are, correct? Okay, well, the calculator will do this for me. Now, obviously, they gave us the one on the left. So what is the one on the left? 0. And more importantly, 0. We want the x-coordinate. So yes, thank you for saying 0 too, because that made me say we want the x-coordinate, right? Because we're working in x's. Okay, and so now what we got to do is we got to find the x-coordinate of that particular point. Okay, and this is a very important calculator skill for you to have. So everybody watch carefully. Second trace intersect. Okay, first curve, and then you're going to guess. So what you want to do is you want to take your scroller here and get as close to that point as you possibly can, and then hit enter again. Okay, and here's what you're going to do. Somewhere on your paper, you're going to write down A comma B is equal to, and then you're going to write down both of these. Okay, and why both? Because at some point we might use the y-coordinate, right? Okay, so at some point we might use that. We want to keep that around just in case, but we know for a fact we're about to use this number, right? And so I'm going to say A comma B is equal to 1.03283, and I would go out a couple of more decimal places than you might normally, because remember, we don't want to round those until the end. And then what does that say, 2.40110? Okay. Now, here's the important part of this right here. Hopefully you haven't hit any more buttons on your calculator and your screen still looks like mine. Your calculator is going to temporarily store these values in x and in y. And so what we want to do is we want to store them in our calculator into something else. Okay, so without hitting any other buttons, hit second quit. And then you can use x, and you want to store that as a. Okay, and there we have it. 1.0328 is now stored in A, and now what the AP exam will allow me to do is write A as my upper bound as long as I have this written on my paper somewhere. Everybody cool with that? Okay, so now we can actually figure out what this is equal to. So on our home screen, we can do Math 9 from 0 to A. And it's probably a good idea if I just erase this right now so we can actually see the calculator. So from 0 to a, and then what do I want to type in?
y2 minus
y2 minus y1. Okay, and that's the beautiful thing about typing those functions into y equals is that I don't have to retype them again. Okay, and so I get 0.9974, and that gives me my area of R. Okay, well, how am I going to find my area of S? What's going to change here? Okay, the bounds are going to change, right? So what are the bounds going to be on my area for S?
It would be a to 2.
Yeah, from A, let me maybe make this a little bit more clear. Let's say over here, this is equal to, what was it?
0.9974.
9974. And so our area of S is going to be from A to what?
2.
To 2. And is it still going to be G minus F?
No.
No, because now at this point, what happened? It flip-flopped, right? The top function became the bottom function, and the bottom function became the top function. And so for S, we're going to have to do f of x minus g of x dx. Okay, so what is that going to give us? Well, if we come back over to our calculator and calculate it, then this is going to be math 9 from a to 2, this time of y1 minus y2 dx. Okay, and I get 1.0069. Okay, and so now if I want to answer the question that they asked, what do I need to do? Add them together. So I can just say, therefore, what is our answer? Well, just to be safe, I'm going to use the numbers that are in my calculator. So that plus that, and I get 2.0043. Now, obviously, could I have written this all out on one line and not done this as separately? Sure, I could have done, right, I could have just written this. Integral from 0 to a of g of x minus f of x dx, right? Plus the integral from a to 2 of f of x minus g of x, right? And this would have been just fine, and then just put the answer. Is that clear? So I didn't have to delineate it like I did. Okay, any questions on that? Okay, so that was method 1. And if that makes perfect sense to you, then you don't really need to pay attention to method 2, but there's a faster way to do this. And so I do want to just explain that to you real quick. Okay, here's what I know, is that at this point, this is called the swivel point, because at the swivel point, the top becomes the bottom and the bottom becomes the top. Okay, and what happens? It changes from G minus F to F minus G. So if I want to stop that from happening and I don't want the sign to matter, how do I make the sign not matter? Absolute value. And so method 2 here is going to be the integral from 0 to 2. So just from here to here. And then if I don't care which one's on top, then I can do absolute value of, and it doesn't matter which one I do. I could do F minus G or G minus F. It won't make any difference. Okay, and so let's just see for kicks if we wind up with the same thing. So math 9 from 0 to 2 of absolute value, and then y1 minus y2 dx, and with any luck, we'll end up with the exact same thing that we got before. And it might take a second for it to calculate, because that's sort of a hard calculation for the calculator to make. Takes a while, and look at that, 2.0043. Okay, so does the AP exam care which method you do? Nope, not at all. Both of them are correct mathematics. Okay, so whichever one that you care to do. Okay, let me just say this, that if these functions were a little more elementary and basic, then the by hand method would be this way, because integrating absolute value is a killer by hand. But because we have a calculator in our hand, this is the easy way. Does that make sense? As opposed to that way where we had to do 2 different integrals. Do y'all follow? Okay. All right, so we go to the next one. I think the next one is non-calculator. If it doesn't say calculator, then that means it's non-calculator. I was really specific on your homework because it kind of goes back and forth between calculator and non-calculator. Okay, so what do we got here? This is non-calculator, so we have to be able to do this by hand. The nice part is that they give us a picture. Okay, the problem with the picture is they don't tell us which one's which. So we have to know some stuff. Okay, so the question is this the cosine, or is that the cosine? Or is this the parabola, or is that the parabola?
The bottom is the parabola.
The bottom is the parabola because it's opening upward, right? And cosine, I know, starts off like that, right? It starts at a max and then dips downwards, right? Okay, so I can clearly say now that this one is g of x and this one is f of x. Okay, and even though I don't have my calculator, because they were nice enough to give me the picture, I know what the bounds are. Is this going to be top minus bottom or right minus left? What looks more straightforward here? Definitely top minus bottom. Are we always hitting the same top function? Are we always hitting the same bottom function? Yes, so we're going to work in x's. Okay, and sort of the hint here is that these are not easy to solve. Right? If they were easy to solve for the other variable, that might be an indication, oh, well, maybe we could do that in y. Okay, but in order to use y, our equations have to be x equals something in terms of y, and that seems like a headache in this particular case. Okay, so find the area of R. This is going to be the integral from what to what? 0 to 2. Okay, of the top function. So what is the top function? Yeah, g of x. Okay, this time, because I'm doing this by hand, I'm going to actually write down what g of x is in my integral. Y'all okay with that? Okay, so this is going to be what? Cosine. And if it's all right with you, I'm just going to write this as pi over 4x. Okay, minus this f of x. Now, when I subtract this f of x, do I just subtract the 2x squared? No, I have to subtract the entire thing. So this is going to be minus 2x squared plus 6x minus 4. Okay.
Be 4 cosine.
Yeah, 4 cosine.
Yes, there's a 4 in front, right? Sorry about that. You're right. 4 right there. Thank you. Okay. So now we have to find an antiderivative. Okay, this back end part is pretty easy. This is the one that's going to take some thought, right? And so this is the U substitution problem that I'm hoping at some point we can learn how to do in our heads, right? Okay, so the antiderivative of this is going to be what? The 4 is just going to stay in the front. What's the antiderivative of cosine? Sine of pi over 4x. But because that's not just x, there has to be a constant here to account for that. And so what's the constant going to be here?
4.
Good. 4 over pi. Okay, so that way when I take the derivative and I get cosine pi over 4x times pi over 4, that's going to cancel out that pi over 4. Are you following? Okay. Minus 2/3 x cubed plus, help me if I make a mistake here, I think 3x squared, and minus 4x, evaluated from 0 to 2. And because this is a free response question, all I really need to do is get these things plugged in and get the heck out of here. Okay, so let's get them plugged in and then get the heck out of here. So this is 4 times 4 over pi times the sine of, if I plug in a 2, this is going to be what? 2 pi over 4? Okay, minus 2/3 times 2 cubed plus 3 times 2 squared minus 4 times 2. Okay, and that's for me plugging in my upper bound, correct? So I'm going to put that part in brackets, and now I'm going to subtract. Now let's work smarter and not harder here. If I plug 0 in to this antiderivative, what is this going to equal? Sine of 0 is 0, correct? Therefore, I don't need to write it. What's that going to be? What's that going to be? These are all going to zero out. Therefore, I don't really need to bother plugging anything in there. Now you need to be careful because it's not always going to zero out. when that lower bound is 0. So just be very careful. That's why I had you consider this, because what if that said cosine? Yeah, now it's 1, right? And so now we're going to actually get something there when we subtract. Is that clear? So be very careful. On an FRQ, we're done. You don't actually have to evaluate that. This is completely finished. Everybody okay with that? All right. That would have been worth about 3 points, maybe 4, on this particular question. Okay, next example is calculator. Okay, so it says let R be the region in the first quadrant bounded by the x-axis in the graphs of ln x and y equals 5 minus x as shown in the figure. Find the area of R. Okay, so if I want to find the area of R, we'll get to the calculator here in a second. Do I want to do top minus bottom or right minus left? Why do I want to do right minus left here?
It's not like below or above.
Yeah, because if I do right minus left, look what happens. I'm hitting the same right and the same left no matter where I am in the region. Do you agree? I'm always hitting the same right-hand function and I'm always hitting the same left-hand function no matter how tall I am in that region. I'm going to erase this here just real quick and show you what's wrong with working in x's. Right here I'm fine until I get where? Here. And so now what happens in this part? I have to change to another top function, which means I have to use a second integral. And I'm going to try to work smarter, not harder, and just do one integral. Okay, so in this particular case, we're going to work in dy. Okay, whenever we work in dy, there's a couple of things here, so maybe I'll write them down. You have to switch the equations. So what that means is that you have to solve them x equals something in terms of y. So you have to solve the equation for x. And the second thing is, what do you have to do on your bounds?
Use y values.
Use y values on bounds. Okay, so it's very important that you make both of those switches whenever you work in y. Now, could you work this in x? Of course you can. Okay, I'm not going to do both methods, but if you did the other method, you would see we're going to get the exact same answer. But I'm going to choose to work this problem in y's just to show you an example of that. Okay, so if I start with this equation, y equals ln of x, how do I get rid of this ln so that it just says x? E both sides. So this is going to be e to the y is equal to x. Okay, and over here, this is going to be what? X equals 5 minus y. Do you agree? Okay. So our area is going to equal the integral. Do we know our bounds right now? Well, we know our lower bound. What is our lower bound? 0, because we're bounded by the x-axis, right? So y equals 0 is our lower bound. Okay, and here in a minute I'll show you how to find the upper bound. Now, if I want to do right minus left, which function is on the right? 5 minus y, and the function on the left is e to the y. Okay, so I'm going to do right minus left. Okay, and now I need to, before I can calculate this, I need to figure out what that upper bound is. So that upper bound, we can just call it a, or you can call it whatever you want. Okay, I just prefer the letter a. Now let me say this very carefully. Please hear me on this. Even though we're working in y's, to get this picture in our graph, we have to put in the original equations. Okay, so if you put in these equations, you're not going to get a picture that looks like this. So you've got to put in the original equations the way they were given to you. Because think about what your calculator says. Your calculator says what? Y equals, right? So we've got to put them in the original way. Okay, so let's go back over here to our calculator and delete out what we had in there from that other problem. And so what are we going to put here? Natural log of x and 5 minus x, right? Okay, and we can just start maybe at a zoom 6 window. That's probably going to be fine. Okay, and so what we're looking for is the y-coordinate of that intersection point. So second calc intersect, first curve, second curve. Okay, and you kind of have to do some maneuvering here to get it to be able to do what you want. Okay, and so if you come over here and guess, which value do we want?
Y.
The y-coordinate. So 1.30655. Okay, I want to go ahead and store that number in my calculator so that way I don't have to type it in again. So where is that going to be temporarily stored? In y. So how do we pull up y? Well, it's alpha 1. So go back to your home screen, and then alpha 1 is y, and then you just want to store that in, say, a. Okay, so there's my y-coordinate stored in a, and so now I want to calculate the integral. So the integral from 0 to a of, now I need to actually write in what it says on my paper. Do you agree? Okay, and here's the other sort of confusing part if you're not careful. Even though I wrote y on my paper, in my calculator I have to put x.
Where did you say it was y?
Where was it? Alpha 1. Alpha 1. Okay, so did y'all hear what I said? Even though I wrote y on my paper, when I type it in the calculator, I have to put x. Does that make sense? So it's kind of like, well, we're changing letters a lot, but hopefully you guys are following what I mean. So 5 minus x minus e to the x dx. And there we have it. We need to make sure that we write our answer to 4 decimal places, so 2.9858. So when I work in y's, a couple of things to remember. First of all, to get the picture, if it's calculator, put in the original equations. Then switch your equations to say x equals, and then use y values on your bounds, your y coordinates. Okay. All right. So we'll go to the next one. Part C, I guess, of this particular question. So there was a part B that I guess is maybe a volume question that I took off, or maybe I just misspelled B with a C. I don't really know. I don't remember. I made these notes a couple of weeks ago. So, all right, what does it say? It says the horizontal line y equals k divides R into 2 regions of equal area. So we have this horizontal line at y equals to k, and wherever k happens to be, it divides this region R into 2 separate regions that have equal area. Okay, and then it says to write but do not solve an equation involving one or more integrals whose solution gives the value of k. All right, so what do I know? I know that this area and that area are the same, okay? Or I also know that this area is half of what we found in part A, correct? So there are actually 2 different ways to do this. So I'll discuss them both, and then you can decide which one makes more sense to you. The first way to do this is to use more than one integral. And so we could do the integral from 0 to a. Make sure that you still have a written somewhere on your paper so that you put a equals. That way you can reuse it in this problem. Does that make sense? Okay. And then for this bottom region, it goes from 0 to k. That's why our bounds are what they are, right? Okay. And then what's our right and left function? 5 minus y minus e to the y dy. And we want that to equal the area of the top region, which is going to be what? The integral from, okay, I think I've messed up. I think I messed up. What did I want this upper bound to be? I wanted this to be k, right? Because that's the upper bound on the bottom of those regions, right? Sorry about that. Okay, and then I want this integral to be from what to what? From k to a. Of the same thing, right? Still 5 minus y minus e to the y dy. Okay, and it says to write but do not solve, right? So we wrote an equation. You don't have to solve it. You just write it. Okay, so what's the other way to do this? Well, we could take the integral from what to what? 0 to k of 5 minus y minus e to the y. dy. So that would represent this area underneath, right? And what should that equal to? A half of what? Answer in part A, right? So what was our answer in part A?
2.98.
Good. Okay, so that's another equally correct way to do the problem, right? Either set up two integrals, okay, one for each of the areas, or just say that one of the areas has to equal to half of the area of the entire thing. Okay? All right, on to that. Okay. So this is non-calculator. So part A says, first of all, let R be the region in the first quadrant bounded by these graphs. So again, they were nice enough to give us the picture, but not quite nice enough to tell us which one is which. So which one is which? F of x is on bottom and g of x is on top. Is that clear for everybody? This kind of looks like the cubic going up like that direction, right? And then we know that sine starts off with this concave down loop type of a deal, right? Okay. So part A is a review question. Write an equation for the line tangent to the graph of f at x equals a half. So what are the two things we need for a tangent line? Point and a slope. Okay, so my point is going to be f of a half, which is going to be 8 times 1/2 cubed, which is going to be 8 times 1/8, which is 1. And then to find my slope, I need to do what? Derivative. So f prime of x is 24x squared. Is that right? Yeah? Okay. And so that means that f prime of a half is 24 times 1/4, since 1/2 squared is 1/4. And so this is equal to 6. And so how would I write my tangent line? Y equals 1 plus 6 times x minus a half. Or anything that's equivalent to that, but remember, starting from now on, once we did Euler's method, we kind of want to start thinking about writing it like this. Okay? And this will be important later on in the spring when we do Taylor polynomials, because you don't know this yet, but this is a first degree Taylor polynomial, and you'll know more what that means in March. Okay, so it's important that we start writing it like that. Okay, part B, find the area of R. So is this going to be top minus bottom or right minus left? It's top minus bottom. Could it be right minus left? Well, sure, but that means we'd have to solve these equations, and then we'd have to find their antiderivatives. So think about solving that. That would include something with sine inverse. You know the antiderivative of sine inverse? Me neither. There's not one. Well, maybe there is, but we'd have to think about it. Okay, so definitely a top minus bottom problem here. So this is going to be area is equal to the integral. What are my bounds going to be if we're going on the x-axis? 0 to 1/2. Okay, we already made the determination that g was on top and f was on bottom, so we want to do g of x minus f of x. So that's going to be what? Sine of pi x minus 8x cubed. Okay, and so now we go to work finding an antiderivative. So again, this is why I put both of these problems on here today. This is the one that we want to try to do in our heads. Right? So what is the antiderivative of that going to say? Negative 1 over pi cosine pi over pi x. Okay, and then minus antiderivative of 8x cubed, bump up to 4 and divide by 4. So that's 2x to the 4th, evaluated from 0 to 1/2. And because this is a free response question, we can plug in and get the heck out of here. So this is going to be what? Negative 1 over pi times the cosine of 1/2 pi. Okay, minus 2 times 1/2 to the 4th. Okay, so there's me plugging in my upper bound, and now I want to subtract and plug in my lower bound. Now my lower bound is 0, so this is obviously going to zero out, but what about this? No, because cosine of 0 is what? 1. So what is this going to say? Negative 1 over pi. Now I'm done. Okay, does that make sense why? Okay, remember earlier that said sine, and when we plugged in 0 it vanished, right? Because sine of 0 is 0. In this particular case it's cosine of 0, which is 1. So we're left with negative 1 over pi. And that zeroed out because obviously 2 times 0 to the 4th is 0. Okay? Yeah, cosine of 90 is 1 apparently. Yes, I heard about this. This is very unfortunate. Anyways, we're on camera, so we shouldn't say anything more about this. All right. Another problem. Let R be the shaded region bounded by the graph of natural log of x and the line y equals x minus 2 as shown in the figure. Find the area of R. Okay, is this top minus bottom, or is it right minus left? Or could it be either one? It could be either one. So let's think about which one is easier in this particular case. Well, I know that in order to do y, I have to switch my equations, right? So I have to solve my equations. Is that easy to solve?
Yes.
Yeah? Is that easy to solve?
Yeah.
Yeah? Okay, but is there any real reason for me to do dy here?
No.
Or am I going to be able to do dx with only one integral?
dx is one thing.
Yeah, check it. Draw some vertical lines here. Do we ever not touch that top function or that bottom function? No. So this is perfectly legitimate to do in dx, right? dy in this case would probably be more work because we'd have to switch our equations first. Is that clear? Okay, so this is going to be the integral. What's our top function? ln of x minus our linear function, x minus 2. Okay, dx, and what are we missing? Bounds. Well, this is a calculator problem, so no problem. We can find it for free by plugging these guys in. Look at that, I've already got natural log of x. So now I type in x minus 2. Okay, I'm going to start at a zoom. I like to start at zoom 4 window whenever it's kind of close to the origin. So zoom 4 is a little bit more zoomed in than zoom 6 is towards the origin. So now I get a really nice picture of what's going on. Okay, so now I need that intersection point and that intersection point. Okay, so I'm going to write down on my paper A equals and B equals. In this particular case, I'm not going to need the y coordinates, okay? But there might be a part lower down that I do need the y coordinates, so sometimes it's smart to save both. Okay, but in this particular case, I can tell you I'm only going to need the x coordinates on both of these intersection points. Okay, so second trace, calculate, intersect. First curve, you kind of have to arrow over a little bit. So there we go, first curve, second curve, and then guess. And so we get 0.158594. What should I do with that number? Store it. So right now it's stored in x. So if I don't press any more buttons, I can just hit second quit, and then x store as A. And now I want to go back to the graph and get the other intersection point. So second trace intersect, and then scroll over to the other one, hit enter, enter, enter. And so which of those two numbers do I want? The x one, right? 3.14619. Okay, and I'm going to store that in B, which is not a big deal. I just do second quit, and then x, store it as B, and there we have it. And so now, here's the nice thing. If I write this on my paper in a place where the reader can see it, so don't do it up near the graph where it's obscure in the corner of the paper, do it where it's clearly visible to the reader. Okay, if you write that down on your paper, now guess what you get to write? A and B, just like that. Okay, so now we can just calculate, right? So we have math 9 from A to B. How did we set this up? Is y1 the ln of x? I think so. So alpha trace y1 minus alpha trace y2 dx. And so we get 1.9490. Okay. You pray for one of these problems on the test, because this was 3 points out of the 9. So I think there were 2 other parts on this question which were also pretty easy that we'll learn how to do next time after Thanksgiving. This is not real hard, right? So let's get really good at this so that if there's a question like this on our BC test, we crush it. Okay, this should be definitely a 7, 8, 9 question for a lot of us, all right? The last time there was a question on the AB test like this was in 2015, and my students averaged 7.8 out of 9. That is a phenomenal number. Okay, so let's make sure that we really understand this and we know what's going on. Okay, this last problem is hard. It is non-calculator, and that's sort of what makes it hard. And it says, what is the total area of the regions bounded between the curves this and that from x equals 1 to 3? Now here's the issue, is it looks like it gives me some bounds, 1 and 3. However, we don't know which curve is on top or bottom, and furthermore, we don't know if maybe it changes somewhere in the middle of that interval. So we got to check. So what we want to do is, first of all, set these equal to each other and solve and see what's going on. Okay, so if I add over the 6x, what am I going to have? 6x squared minus 12x equals 0. So if I factor out 6x, that's going to leave me with x minus 2, I think. So I get that x equals to 0 and x equals to 2. And this is the big red flag right here, because that 2 is right in the middle of 1 and 3. And so between 1 and 3, there's a swivel point. There's a point where the top becomes the bottom and the bottom becomes the top, which with a calculator wouldn't be a big deal because we could just use absolute value and be done, right? Okay, but integrating absolute value by hand is a nightmare. So therefore, what we're going to do is we're going to set up 2 integrals. The first integral is going to be from 1 to 2. And the second integral is going to be from what to what? 2 to 3. Now here's the issue, is I don't have a graph. I don't have a calculator. So I can't determine which one's on top and which one's on bottom. Okay, and I don't have a real good intuitive sense based on these equations which one's going to be which. Like I don't know really what that graph looks like. So here's the thing. I'm going to guess which one's on top, and how am I going to know if I'm right or not? Because I should always get a positive value for area between 2 curves. Always, always, always. The area between 2 curves should always be positive. Should area in general always be positive? No. But when we're talking about area between 2 curves, that area should always be positive. So I'm going to take a guess, and if I'm wrong, then I just flip the sign. No problem. Okay, does that make sense? All right, so we'll take a guess. We'll say that 6x squared minus 18x is the top, and then minus the bottom is negative 6x, correct? Okay, so let's go this way since I have something down here. So this is going to be what? The integral from 1 to 2 of 6x squared and then minus 12x, yeah? Okay, antiderivative. So bump up to x cubed, divide by 3, that's 2x cubed, minus bump up to 2 and divide, so that's going to be 6x squared, evaluated from 1 to 2. And so what am I going to get here? 2 times 2 cubed, 16, minus 2 squared 4 times 6, 24, and then minus 2 minus 6. Okay, which is what? Negative 8 minus negative 4, which is -4. So did I make the right guess?
No.
No. Not a problem. I just know that this is going to end up being a +4. Okay, but am I done? No. Now I have to do the area between 2 and 3, but guess what? Now I know that this was wrong, and so for this interval, it's going to be right. Don't you agree? Okay, so in this case, now we know it's going to be correct. So I'm just going to skip to the punchline here. This is really -12x dx, and guess what? We already did a bulk of the work because we found the antiderivative already, so that was what? 2x cubed minus 6x squared, evaluated from 2 to 3, which is what? 3 cubed is 27 times 2, 54, minus 3 squared, 9 times 6, 54. Is that right? Okay, minus, plug in 2. Well, I already did that. It's minus -4, right? Which is +4. And so now to get the total area between these two curves from 1 to 3, we add what we got for both integrals, and we wind up with this nice fancy number of 8. Okay, is that clear? Let me stop the video now.